Hello everyone, welcome back to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. Today's video is going to be a video that's part of 3 or maybe even 4 videos. What I want to show you cannot be compressed into a single video. It would be too long even for my standards. So I'm going to show you just a few aspects right now and several others in the second version, the second video and the third video as well. So the idea is that I wanted to design and create myself a sort of a multimeter that is able to measure 4 things at once and calculate the efficiency of DC-DC converters. And this is what I'm showing you now on screen. It's not completely finished. I still need to design and 3D print a plastic case, but as far as the electronics are concerned, they are finished. The idea is that if you use DC-DC converters, you will definitely want to, and if you plan to use DC-DC converters for a longer period of time, especially in a context like we are trying to prepare, where we are producing our own electricity, and obviously we do not want to waste too much electricity, we would be concerned with how efficient those DC-DC converters are. It doesn't matter if you buy DC-DC converters from the market or if you manufacture them yourself. It doesn't matter if they are step down or step up. The efficiency matters to a certain degree, and just because you buy a DC-DC converter from the market does not mean that they are efficient, that they have a 90% or higher efficiency level. No, not at all. So, of course, measuring efficiency can be done manually, but there are some disadvantages to that, and yeah, I wanted a more automatic and a more simple solution. So I thought of a single device that is able to perform 4 measurements at once and do some calculations as well, so that this problem gets solved in a more elegant manner. And this is what I've created. It's not super great, it's not super high precision, but definitely the work that I've done has been good enough for a first version, so that now I know where I did some mistakes and how I could improve this in the future. And the nice thing is that those mistakes are contained in a single board, so if I replace that particular board, then the whole device will become better. Anyway, this is what I will explain to you in this video. In this video, I'm going to basically make an overview of the whole problem and solution that I present to you. And we're gonna start discussing about the power supply of this entire project, because I wanted this to be powered by an old phone accumulator. And of course, I needed some circuits for that. So yeah, stay tuned if you think that this project is interesting for you. Before we dive into today's circuits, please allow me to thank the sponsor of this video, which is PCBWay, and at the same time to give you some good news. They are currently organizing their 6th project design contest, and you can participate too. They have 2 themes this year. You can either choose to participate in an electronic project or in a mechanical project, such as a 3D printed object or a CNC machined one from metal. You can apply and upload the necessary files until 15 January. Let me show you. Until 15 January 2024. And if you're one of the lucky winners, you will find that on 8th March 2024. You can find all the details and the rules of the contests on the contest webpage at PCBWay. And of course, in order to help you build your desired PCB board or physical object, you can choose to employ PCBWay's services. They can assist you with creating with their PCB manufacturing services, PCB and components assembly, if you want those small semi components assembled by them instead of you struggling to solder them on the board. Semi stencils, as well as 3D printing, injection molding, or even CNC machining. Both the link to PCBWay and their contests are in the description. Thank you PCBWay for sponsoring this video. Good luck with the contest if you choose to participate. And now let's get started with the circuits that I want to show you. So, like I said, when we have a DC-DC converter and we would like to measure his efficiency, what we can do manually is basically to what we can do anyway, regardless of whether we're choosing a manual or a more automated solution, we need to have a power source, right? A power supply of any kind that we feed the DC-DC converter, and then at the output of the DC-DC converter we will need some sort of artificial load, electronic load, or however you want to call that. With the power source, of course, we need to power the DC-DC converter, and with the artificial load, we are, and preferably a variable artificial load, we will be trying to pull various currents and see how the DC-DC converter does. In order for us to calculate the efficiency, we need to measure 4 things at once. Both the input and output voltage and the input and output current. So for that, in order to perform a manual measurement, we need to basically take 4 different multimeters and place them 2 at the input, 2 at the output, right? Set the power source at a certain voltage, set the DC-DC converter to output a certain output voltage, and then draw some current with the artificial load, write down on a piece of paper all 4 measurements with the 2 voltmeters and the 2 ampermeters, and then calculate, these values we would put in a formula and calculate the efficiency. And we need to do this several times because the efficiency is not fixed, is not a constant. It varies depending on the input voltage, output voltage, and output current. So we would need to do multiple sets of measurements at different input voltages, different output voltages, and with different output currents. Of course, this would take a bit of time. It would make us fill an entire page full of, an entire paper page full of details, full of numbers, which would then be needed to either perform some mathematical calculations manually on a calculator, or we would need to input those numbers into an Excel table and have them more automatically calculated. This is a first problem because when we have 4 multimeters on the workbench, they occupy a lot of space. They also need, they also have various cables, and those cables occupy even more space and bother us on the workbench. Those cables also have, typically, they don't have a negligible resistance, sadly. They have a resistance that will start to matter at higher currents because they will develop quite a bit of millivolts of voltage drop potentially even hundreds of millivolts, which is gonna be, you know, significant. So yeah, those are a first set of problems that we would have. Of course, the method is working. We can use this method, but it's not elegant. There is, however, another problem with this manual method, which is the fact that the internal resistance of the ampermeter matters, at least the ampermeter on the input of the DC-DC converter. And I've come into this problem when I tried to test the DC-DC converter that I used here in this project, and that is, well, if we elaborate this problem a little bit, so we have the power source, power supply, whatever. We have the ampermeter that measures the current that goes into the input of the DC-DC converter. But this ampermeter has an internal resistance, and this internal resistance depends on what is the maximum current that we can measure on that particular scale of the ampermeter, especially if we're using a manual switching multimeter. Okay, now if we set the ampermeter on 200 milliamps maximum, of course this internal resistance will vary from multimeter to multimeter, but the multimeter that I was using had 5 ohms of internal resistance at 200 milliamps and 25 ohms at 20 milliamps. That's quite a lot, because this resistance basically plays in series with the inductor of the DC-DC converter. And as a result, it might be that the DC-DC converter either will require more time to charge with a magnetic field, this inductor, and therefore the efficiency drops, or the DC-DC converter in some cases will not be able to function, like in my case. He will simply not be able to function properly to give us on the output a stable voltage, because this internal resistance of the ampermeter is just too high, and the inductor never managed to charge himself with enough energy to supply it to the output. So the entire DC-DC converter doesn't work anymore, which happened to me. Now, this problem could potentially be mitigated if we use the multimeter on the 10 amps range, because on the 10 amps range we have a very small internal resistance in the order of hundreds of milliohms, maybe even less at some multimeters. However, the problem is we lose resolution and precision, I would say, because on the 10 amp range 100 milliamps becomes a small value. Anything less than 100 milliamps is also going to be a problem to rely on. So the entire the measurement becomes better for the DC-DC converter, but worse for the overall calculation that we need to do in the end. So yeah, this is something that we need to be aware of when we are performing this sort of manual measurement. So obviously a more automated solution, if possible, is to be preferred. So this is what I'm presenting to you here. What I've been trying to do and accomplished to a certain degree is basically create a device that measures both voltages and both currents at the same time. This device relies on the fact that we are having a common ground for all of these entities here. So we have a common ground for the DC-DC converter, for the power supply, for the load at the output, and for the entire multimeter as well, which means we will not be able to measure inverting DC-DC converters or power supplies with isolation. Those will not be able to be measured here, although we probably don't care about those, or if we want to measure those, we will essentially create a different device, or we will think of a different design for those problems. I only cared about measuring DC-DC converters efficiency, step down, step up, not inverting ones and not isolated power supplies. And for that, I'm using an Arduino Nano, basically. Our Arduino Nano has 8 different ADC channels that we can use. I've used all 8 of them. 4 of them for measuring the input voltage and current, another 4 for the input voltage and for the output voltage and current. Of course, we cannot just feed those directly. We need to have a special circuitry that first of all converts the current into voltage, and then it also steps down the voltage accordingly, because Arduino Nanos can only measure up to 5 volts maximum. So I have a circuit that does that. It's quite a bit of a circuit, quite a few components here, and I will discuss them in the second part of this, well, in the second video of this series. Okay. An Arduino Nano is also connected to a Nokia 5110 LCD screen because it's cheap, it can be found on the market, and I had a few of them already. They connect via, I believe, CPI data bus, CPI protocol, and these LCD screens can display up to 4 different lines of informations at once. So I was able to display all of the informations that I needed at once on this relatively small LCD screen. And I wanted this entire device to be powered from an old lithium 3.7 volts accumulator that I got from a very old phone that still works. So I wanted to reuse this accumulator. I didn't want it to buy a new one, and I didn't want it to buy I didn't want it to use a standard battery. I wanted to use an accumulator so that I can recharge him. Okay, so of course I also needed a power source for that, which requires 3 different stages. Low battery indicator, so that we know when, you know, the accumulator has discharged himself completely and needs to be recharged. Another voltage protection, because as with lithium or any other kinds of accumulators, really, we need to prevent the discharge below a certain voltage level. And a step-up converter, which I just wanted to design and build myself. Okay, so this is pretty much the overview and how, on a great line, how this device looks like, what I've made, and yeah, what I'm going to show you in these next 3 videos. So in this video, I will want to focus only on this power supply that powers everything, powers the Arduino, indirectly the LCD screen, although the LCD screen draws 3.3 volts from the Arduino himself, and this signal conditioning board, which is also powered from 5 volts. In the next video, I will discuss about this signal conditioning circuit, and in the third and final video, I will discuss the others, which is the LCD screen and the Arduino Nano connection and the software involved. So, regarding the power supply, like I said, first things first, we have a low battery indicator that, so we have the accumulator in series with an on-off switch. Of course, we don't want to leave him on at all time. And the first thing that we need to have is a low battery indicator. Essentially, we want to have a LED that turns on when the battery is too low and normally stays turned off. I'm not gonna go into great details about this this circuit, because this circuit has been discussed on a video made in 16 December 2022. I will put the link in the description. The only difference between this version that was presented then and this version that I'm presenting now is the fact that I recalculated a bit the resistors to work for a 3.7 volt nominal voltage lithium accumulator. Whereas back then I used a 9 volt battery, so of course the resistors had a bit of a different value, because the threshold at which the LED needed to be turned on was of course different. Next stage is the undervoltage protection. Now, I haven't discussed about this in a dedicated video, so I'm going to do a little bit of explanations here. The idea is that we use a P-channel MOSFET to turn him on and keep him on normally when the voltage is good enough on the input, so that in turn he gives this voltage, this power to the rest of the circuit. However, we will turn off this channel MOSFET when the voltage drops below a certain level. And we also don't want to have a slow turn off, because then we would put the MOSFET into linear region. We want him to work in a switching kind of way. So on the input we have first an NPN transistor polarized by a 120 kilo ohm resistor that basically is by default is turned on to the maximum, which pulls down the gate of this MOSFET, which turns the MOSFET on, because the gate of P-channel MOSFETs, the P-channel MOSFETs get to be turned on when their gates are below their source in terms of potential. Okay, this is why we have a very small resistor here, 2.2 kilo ohms in the gate, and we much larger resistor here between the source and the gate. This 82 kilo ohm resistor is needed in order to turn off, to make sure that this MOSFET gets turned off when this bipolar transistor gets turned off. Okay. So this P-channel MOSFET will be turned on by default, because this transistor will be turned on by default. What happens is that when the voltage drops below a certain level, this transistor will be shut down by this middle transistor, which is actually a part of a Schmitt trigger, a simplified Schmitt trigger. A normal Schmitt trigger with two bipolar transistors, if you search the schematic on the internet, you will find with 5 transistors, but the schematic can be simplified at only 3 transistors. This 120K one, this 151, and this 3.3K transistor. So, how does this whole Schmitt trigger works? Well, we have a resistor divider here, 390K with 100K, that feeds a certain voltage in the base of the first bipolar transistor. When the voltage is high enough, this transistor will be turned on. Because this transistor has his collector in the base of the second transistor and they have a common emitter, this first transistor will basically close and maintain closed the second transistor, which in turn will allow this third NPN transistor to be turned on, and therefore power will be outputted from the entire circuit. However, when the voltage drops too much, and I've calculated these resistors to be at around 3 volts, so when we have around 3 volts on the power rails, on the input, the first transistor will no longer be able to sustain himself to be turned on. So he will turn off, enough so that the second transistor will turn on, because his base will no longer be pulled low towards his emitter. When the second transistor turns on, he will in turn turn off the third transistor, which will allow the gate of the MOSFET to jump up towards the positive rail and therefore shut down the MOSFET. Okay? And this is how the undervoltage protection happens. And because we use a Schmitt trigger with these resistor values, the voltage, the entire circuit has turned off at around 3 volts of input voltage. However, in order to turn back on, the input voltage has to go back to around 3.4 volts. So the voltage can start to increase back. The circuit will still remain shut down, and it will not turn on again until the input voltage goes above approximately 3.4 volts, because there is a hysteresis effect that happens due to this 3.3K resistor. Okay. So this is how the undervoltage protection works, and it's absolutely mandatory when we are using any form of accumulator, whether it's lithium or lead or whatever other kind of accumulator. Okay, so now that we have protected this accumulator, we have another problem that we need to solve, and that is, well, we have anywhere between 3 and 4.2 volts given by the accumulator himself. Of course, I'm assuming that we use a single cell accumulator, and that's what I used. I used an old battery accumulator. But we need 5 volts for the rest of the circuit, because Arduino works with 5 volts, and the rest of the circuit also needs 5 volts. So, in order to have 5 volts out of a voltage that varies between 3 and 4.2, we need to have a step-up converter. Of course, theoretically, you can just go and buy one from the market, especially one that is decent in quality. If you prefer that way, sure, go ahead and do that. I wanted, because I want to study DC-DC converters anyway, I wanted to build my own DC-DC converter with discrete components. Even though it's not such a great, efficiency, but nevertheless, I just wanted to build my own. So this is what we have here on this lower portion. I have a DC-DC converter that generates about 8 volts. That is then being stepped down by a linear voltage regulator to make sure that we have an absolutely smooth 5 volts power supply for the rest of the circuits. Now, the workings are relatively simple, and I'm going to reference another video of mine that I created relatively recently on 29 September 2023. Better replacement for 555 timers was called. And in this video, at some point above 20 minutes, I explained how we can have a constant frequency variable duty cycle signal generator, essentially square wave signal generator, that we could not have created with a 555 timer. And basically in this entire video I'm presenting how you can have a simple open collector comparator such as LEMET 393 or 339 to generate square waves and have them at fixed frequencies and variable duty cycles. Well, the beginning of this DC-DC converter is essentially that, because we need to generate a square wave to be able to switch our inductor. I have used such a circuit with one comparator, you know, and all the associated components. So, because I've created this dedicated video, I'm not going to go into great details about how he works. I will put the link in the description as well, so that you can jump there and analyze this particular circuit before moving forward. So I'm generating a roughly 100 kilohertz signal, feeding the more or less linear ramping. It's not quite linear, but anyway, the ramping voltage of the capacitor. I'm feeding that to the negative input of the second comparator. And on the positive input, I have another voltage that I generate with a voltage divider here, this 18 kilo ohm and 12 kilo ohm resistor. This goes up to, I don't know, 40% of the power supply voltage. This needs to be less than 50% because the voltage on this capacitor goes up to about half of the supply voltage, and we need this to not go so much. This other voltage we need to not go so much, because then we would be in a situation in which this this inductor will get turned on and be kept turned on continuously, which we will not want, because he will start to draw a bit too much current. So 18 kilo ohm and 12 kilo ohm, I have determined experimentally that it is good enough for what we want. It gives us about 40% voltage maximum here, which is still below 50%. We have a 220 nanofarad capacitor here in parallel with a 12 kilo ohm resistor. Again, determined experimentally. I don't really have actual formulas for these. I just swapped different capacitor values, and I saw which one was better than the other. This capacitor ensures that this voltage here also ramps up in time, instead of having an instantaneous voltage that is at maximum. We need this ramping up because if the voltage ramps up here on the positive input of this comparator, then on the output we would have a constantly increasing duty cycle. Okay, and we also have another resistor here, a small resistor, 1.3 kilo ohm, in the collector of an NPN transistor. When the NPN transistor will be turned on to the maximum, basically this entire voltage divider will change, and this capacitor will start discharge, and by him discharging, we will have a decreasing duty cycle on the output. And these are all part of essentially the feedback circuit that ensures a somewhat constant voltage on the output. This comparator, which has an open collector, by the way, so the output is a collector of another NPN transistor, the emitter being at the ground. When the output is shut down, so the collector does not pull down to the ground, then this NPN transistor will be turned on, which will power this N-channel MOSFET, which will be turned on to the maximum and will allow current to flow into this inductor and charge the inductor. Then when the comparator will put his output down to the ground, because he will turn on the last NPN transistor inside of him, then this transistor will turn off, and at the same time this Schottky diode will start to conduct and will discharge whatever charge we have charged this internal capacitance of the gate source of the MOSFET, will discharge as fast as possible and will turn off this MOSFET as fast as possible. Okay, so this is how we switch current on and off through the inductor. And because we switch the inductor down to the ground, of course the The voltage that will be generated when this MOSFET is off will be in series with the input voltage, and therefore we will have a higher voltage here than the 3.7 volts of the lithium accumulator. This is the principle of any step-up DC-DC converters. Okay, we have another Schottky diode here to basically make sure that we don't short circuit the output when this MOSFET is turned on. 100 microfarad capacitor here seems to be good enough. And then for the feedback portion of the circuit, we have a 7.5 volt Zener diode in series with 150 ohm resistor. This makes sure that the voltage on this resistor basically is total voltage of the output minus this 7.5 volt, so that this transistor gets turned on at around 8 point something volts. And by him turning on, again, he pulls down to the ground the plus input of this second comparator, which in turn makes it so that this capacitor will get to be discharged. So the duty cycle here will decrease. By decreasing the duty cycle, we will, inject less energy into the inductor, and therefore the output voltage will decrease. This is a very primitive form of step-up converter. It's not super stable. Like if we would take a look here at this voltage, it varies quite a bit. I wouldn't say it oscillates, but rather it has a significant ripple. In order to make this a little bit better and eliminate high frequency spikes, I've used an extra LC filter, a 1 millihenry with 10 microfarads. This is one of those tiny inductors that look like a resistor, low power, because we won't pull more than, I don't know, 25 milliamps out of this DC-DC converter, so we don't need high power inductors. And this filters quite a lot of the high frequency, the high frequency signals that we still find on the output of this DC-DC converter. This inductor here has around 420 micro Henry inductance. It doesn't have to be 420, it could be less. I basically took a ferrite core, I wound my own inductor, and in the end it turned out to be 420 micros because I put a bit too much turns and I left it there. So I created my own inductor for this DC-DC converter. Of course, you could use a standard inductor that you find on the market that you can just buy. I just had plenty of cheap ferrite cores that I bought from someone secondhand, so I used, I created my own inductor here. And in order to have a smooth 5 volts on the output, because here we have around 8 volts, by the way, in order to have a smooth output voltage, we have a 78L05 linear regulator. Okay. And that's it, problem solved. If I am to show you, hold on a second, the ripple here, after this LC filter, the ripple is a lot better. It's still about 120 millivolts, but it doesn't matter because we have a linear regulator beyond that point. But what matters is that we have no high frequencies whatsoever. This looks a bit like a sinusoidal form. It's not a sinusoidal one perfectly, but anyway, it's something like that. And frequency is about 700 hertz or so. Don't take into consideration this 1 kilohertz. He wasn't measuring. He wasn't performing an accurate measurement. I don't know why he measured 1 kilohertz. We have 500 microseconds per division, and one full repetition is at around 1.3 1.3, 1.4 milliseconds. So that's the equivalent of some 700 hertz of ripple. Therefore, no high frequency, which is good. I actually wanted to not have any high frequency spikes whatsoever, because that would affect all the measurements that we do with that Arduino. Yeah, and this is pretty much it in terms of, you know, creating a primitive step-up converter that basically give us the freedom to choose almost whatever component we want here. As long as we have open collector comparators, it can be any model. These bipolar transistors also could potentially be any model of transistors. The MOSFET needs to be an as low. So let me open just a second the datasheet and explain to you why I chose this particular BXT 420 per channel MOSFET. N-channel MOSFET. This MOSFET needs to be chosen based on two criteria. One, as low RDS on as possible, so resistance drain to source. And two, this MOSFET needs to be turned on at the gate source voltage as low as 2.5 volts, because on the input we have 3 volts after all. A lot of MOSFETs require around 5 volts to be turned on completely, and this is a problem. So we need to pick an N-channel MOSFET that gets to be turned on at around 2.5 volts. So I chose a Bridge Lux 420N03M for two particular reasons. Like I said, gate threshold voltage. We see here that in order to have 2 amps, which we will never have in this project, but anyway, we can have as low as 2.5 volts gate to source voltage, and we will still have no more than 70 milliohms of resistance, which is great. I mean, this resistance is small, therefore it's great. This is why I chose this particular model. Of course, it could be a different model, but you know, go into the datasheet and search for gate to source voltages of 2.5 volts. If you don't find them, then you will either have to search for a different transistor or perform your own tests to measure this resistance drain to source when the gate to source voltage is 2.5 volts. Because again, in this project, since we are powering this from a lithium accumulator that goes anywhere between 3 and 4.2 volts, we cannot rely on higher voltages than 3 volts. Okay, and even 3 volts we won't have them, because you know, when this transistor will be turned on, there will still be a bit of a collector to emitter saturation voltage, so it will be less than 3 volts. So this is pretty much it when it comes to, you know, creating your own power supply for this particular project. Again, feel free to just pick a step-up converter from the market if you choose to do so. I'm just presenting to you my own ways, because I like to create everything from the ground, because if at some point something breaks, I know exactly what to do and with what to replace that something. So that's pretty much it for today's video, because I don't want him to get longer, and if I start explaining to you the other aspects, it will go way above 1 hour. So that's pretty much it. In the next videos I will show you basically how we can perform the measurements of these input-output voltages and currents. So essentially we will take a look at this particular circuit. So yeah, let's just leave that for the next video, which is going to come in a few days. Hopefully by then I will also have managed to create a plastic case for this device so that he can look a bit better, because right now, like you see in this image, I only have, you know, all the boards separated and just put on the table, and that's it. Of course, I need to build a plastic case for this entire device. So yeah, we will see each other in a few days. Thank you very much for watching this video. I hope you found him useful. If you did, please like and subscribe to this channel and to this video. Also, I want to thank the people who are sponsoring or who are helping me on Patreon. If you would like to help me build more projects in the future, help them build faster than I'm able to build them right now, you can consider supporting me on Patreon. The link is in the description. Thanks again, and I will see you soon in the next video when we discuss the next steps of this device. Bye bye. Have a nice day.